Good morning. Thank you for joining us for an ACME seminar today. I'm delighted to introduce Professor Katherine Faber, who is the Simon Ramo Professor of Material Science at the California Institute of Technology. She earned her PhD in Material Science and Engineering from the University of California, Berkeley. Prior to joining Caltech, she held appointments at The Ohio State University and Northwestern University. Professor Faber is a fellow of the American Academy of Arts and Sciences, a distinguished life member of the American Ceramic Society, and a fellow of ASM International. Among her awards are the Society of Women Engineers Distinguished Educator Award, the Toledo Glass and Ceramics Award, and the John Jepson Award, both of the American Ceramic Society, and the Edward DeMille Campbell Memorial Lecture of ASM International. She served as president of the American Ceramic Society in 2006 through 7. While at Northwestern University, she co-founded and co-directed the Northwestern University Art Institute of Chicago Center for Scientific Studies in the Arts, where she advanced materials characterization and analytical techniques are used in support of conservation science. Her research interests also include the fracture of brittle materials and the mechanism by which such materials can be toughened, ceramics for energy-related applications, including thermal and environmental barrier coatings for power generation, porous solids for filtration and flow, and cultural heritage science. Without further ado, Professor Katherine Faber.
Well, good morning. Okay, well, first of all, thank you for this invitation to speak with this group. It's wonderful that you can draw people from a number of departments and beyond. Today, I'm going to talk about probing pore space, and Caltech actually manages the Jet Propulsion Lab, and so there are always people here on campus talking about probing space. I'm going to go in the other direction and look at microstructures, and particularly those that contain pores. And so with these materials, we try to craft specific architecture that contain porous materials, that contain pores. And what I'd like to do is also talk about how some specific designs relate to both medicine and energy related applications. So let me now start with what I call the whole truth, or the truth about holes, if you will. And that is, I grew up in this materials science community, particularly focusing on mechanical behavior. And as I was learning, and in the early days of my career, if you were working on mechanical behavior, the last thing you would ever want in a ceramic material was a pore. And the reason is that pores can act as flaws, and the strength of a material is inversely proportional to the square root of the flaw size. So because of that relationship, one would want to avoid this at all costs. Pores also prevent optical transparency. They reduce a lot of mechanical properties, not just the strength, but the hardness, the stiffness, and wear resistance. And they also tend to reduce thermal and electrical conductivity. However, as the field has advanced, we know that porous materials really enable a broad array of applications. And to give you a sense of that, in terms of porous solids, they're absolutely essential in things like fuel cells and batteries, in catalyst supports, your catalytic converter, which seem to be a hot commodity these days, are made in a way where you have these flow-through channels as you would need, and those support the catalysts that are needed for keeping some of the nasty substances out of the environment. They can be used for bone scaffolds and microfiltration, and of course in thermal management, where that low thermal conductivity is then used to an advantage. So with that in mind, we need some sort of way to describe these pore networks, because it's not just, as you saw in this previous slide, these pore arrays can have a variety of shapes and sizes. So it's not just how much porosity is there, shown here in terms of fraction, but we also need to think about pores in terms of their size distribution, their surface area, their tortuosity in a specific application in which the pore pathway can be quite rough. And in fact, we can get a measure of that. The degree of order in the pores. So you saw in the catalytic converter that the pores are highly ordered, whereas in an application for bone scaffolds, they needn't be as well ordered. And we're also interested in connectivity of the materials, which you see here in this three-dimensional image, where the green here shows continuous porosity. So all of this then comes into play in terms of how we process these materials. And so that will be a lot of the focus of my presentation today. So just to give you a sense of some of the things I've worked on, it turns out as I look back that I've worked on a variety of porous solids. Some have to do with wood-derived materials where we can convert them to silicon carbide or to carbon, and we end up with microstructures that look like this. They're known as biomorphic solids because we replicate what might be seen in a wood-based material. We've used, working with some industrial partners, we've looked at acicular mullite here, and you see these beautiful needle-like structures that can be produced to look almost like pickup sticks. And of course, with the advent of additive manufacturing, we can also create porous structures as they're seen here in a very ordered array. My focus today is going to be on these materials shown here in the bottom center. These are known as freeze cast solids, and they're produced in which we, by way of forming a template and then removing the template. And this specific one is produced to form a silicon oxycarbide. So the two themes that I want to focus on today are, first, how can pore networks be tuned to control flow and filtration in the body? And secondly, how can pore networks be tuned to favor deformation of a material over fracture? So let's start. So this tunability, as I mentioned, is a critical feature. And the process that we have used is known as freeze casting. And we're relying a lot upon an understanding of the solidification process. I have to admit that in the ceramic community, we don't think a lot about solidification, in part because many of these materials are so high in terms of their melting points that we try to make them without going through a melting and solidification process. Instead, we do a lot of solid state processing. But in this particular case, we had to learn about solidification. And what I show here in this pressure temperature diagram is really a map which describes the solidification process. So we can do this in one of two ways. We can start with a suspension of powders in some sort of dispersing fluid. It can be as simple as water. We have also found and concentrated a lot of our effort in using pre-ceramic polymers that we put into solution, and we cross-link it. Now, this is generally done at ambient temperatures. And at that point, we then decrease the temperature in the system. And specifically, for our interest here, we do this directionally. So one might produce a mold, take that suspension or solution, pour it into the mold, and that mold is sitting on a cold plate. And so the solvent or the dispersing fluid now begins to freeze. And it freezes in a directional manner, as you see here with these light colored lines. And it's basically pushing either the pre-ceramic polymer or the powders out of the way. And so that is conducted until the solvent is completely frozen. And then we move to lower pressures and sublimate then the solvent. We generally have to go through one more step, and that is if we had a powder, we would sinter it or fuse those ceramic powders together to form a robust solid. But again, the pore is maintained, that pore network is maintained, as you see here, that we have created through the freezing. And alternatively, if we're working with a pre-ceramic polymer, we pyrolyze this. So we end up with a generally very lightweight and porous solid that is has some degree of robustness because of this final step. So one of the things in terms of this tunability that is almost intuitive is that the pore sizes are going to depend upon how fast you conduct this solidification process over here. So if you freeze really quickly, the diffusion lengths are pretty small, and so you end up with small pores and relatively small pore walls. If instead this freezing front goes through the material pretty slowly, we're basically allowing the system to have more time for that separation between the fluid and the pre-ceramic polymer or the powder. And so you end up shown here with larger pores and larger pore walls. So that's almost intuitive. Okay, we also, by virtue of the fact that we're directionally freezing this, we also have some control over the directionality. And in fact, we can control that by, in addition to this cold plate, by putting some sort of a template at the base of the cold plate, where we can define then the places where the solid will nucleate. And we see this here. This is just a series of colorized images that have told us which pores are standing straight up, which are the ones in green, and which are sort of off axis here. And so with the appropriate template, we can get a structure where you're looking at the surface, this colorized surface, to tell you what percentage of the pores are just basically facing out at you. And we can do that, as you can see, quite successfully compared to the image on the left, where the purple indicates that the pores are off axis. So the takeaway message for this is that slow freezing produces larger crystals. The pore size also decreases if you put more polymer in there or more powder in there due to that increase in the solid fraction. And we can also change the pore structure and wall thickness by templating with some degree of directionality. Okay, so let's now go a step further. What else can we control? Because at the start here, I told you of all of the things we wanted to control, not just size and fraction, but connectivity, et cetera. And so to think about that, first I want to tell you a little bit about this pre-ceramic polymer system that we use. Paulo Colombo has done some extensive work on pre-ceramic polymers, and he and a couple of colleagues wrote a very beautiful paper that describes a great deal of work on these pre-ceramic polymers. This figure up here in the middle is a demonstration of the various pre-ceramic polymers that range from polysiloxanes to polycarbosilanes that allow you to make a lot of silicon-based ceramics. And that ranges from ceramics that include silicon, aluminum, and boron, just by virtue of the pre-ceramic polymer that one uses. We focus our work on the polysiloxane, and the reason is that when the pre-ceramic polymer converts to a ceramic, there's a pretty high yield, and that's to our benefit, okay? So this really enables, this scheme here enables a wide variety of techniques and materials. I mentioned that these are cross-linked. That step occurs over here in the solution step, and you can do that either using temperature or via a catalyst, as we often do. And then this can be pyrolyzed in the regime of 600 to 800 centigrade. And some of these materials crystallize as low as 1,000 degrees. Excuse me. Because of that carbon network, sometimes these materials are often resistant to crystallization, and many of the materials that I'll show you here are largely an amorphous silicon oxycarbide. Okay, so let's now think about the tools that we have in hand to give us a greater sense of tunability. What I'm going to focus on in terms of these tunability methods is, first of all, the choice of solvent that we use for this solution step. I'm also going to show you that we can control the temperature gradient in the freezing process. And the other method I'm going to focus on today is coarsening the structure, and in doing so, changing the morphology. So in this, I don't have time to talk about all 5 here, but we'll pay attention to 1, 2, and 4 here. So one of the things to think about in terms of the freezing process itself has to do with how fast a freezing front is moving through the solid, and also the temperature gradient that we have imposed. What is the temperature of that cold plate versus that at the top of the solid? And if you look at the solidification literature, one of the things that is quite informative is this map that you can find in Marty Glicksman's book on solidification. And this is known as a solidification microstructure map. And what we see here are various regimes that describe the interface. If you can freeze things very, very slowly over a given temperature gradient, the freezing front is basically horizontal, and but it requires very low freezing front velocities. If you increase this velocity, basically there are perturbations along the freezing front, And you begin to see this unstable freezing front that at first appears cellular, which is what you see here on the left. And if you go further, you end up seeing what I consider to be very beautiful dendritic structures. So basically, if we can follow this map, if we have control over freezing front velocity and temperature gradient, we can move microstructurally through this map. If you go too far, you just get an equiax structure. So that's one important feature of all of this, that these parameters are at your disposal to then control the shapes, the morphology of these pores. Of course, the crystal structure of the solvent that one uses plays a role. If you look at the crystal structure of ice, as I've shown here, when that begins to freeze, we have, you can see in this diagram that there are preferred growth directions. And if you were to use then water to produce these porous ceramics, you'd end up with these structures that look as they do on the right here, where the solid material almost looks like a deck of cards. These are lamellar type structures. And the ice crystals that have now been sublimated would be between those layers. Now, there's another aspect here that plays an important role. And the parameter that we have used to help us define this is known as the Jackson alpha factor. And basically, it's this Jackson alpha factor that will tell us that on solidification, whether an atom will attach to a surface in a very preferred place, as shown here in this diagram on the left, where basically we're developing a highly anisotropic structure, or if on solidification, that atom, as it attaches to the solid surface, doesn't really care. And you would end up with this below, where you have a structure with low anisotropy. Excuse me. And so it is this Jackson alpha factor that gives us a clue in all of this. It's related to the number of nearest neighbor sites. It's related to the total number of nearest neighbor sites of an atom in a crystal. But the factor that we have looked at carefully is the latent heat of fusion, or over the melting point shown here. And you can think about this in terms of the free energy, plotted here as a function of the occupied fraction of surface sites. So if alpha is very, very high, basically the atoms on solidification would prefer to be in either one of two places, and those are the ends then of this particular curve. Whereas if this Jackson alpha factor has a low value, there are many, many sites in the solid where an atom would be stable. And so we would expect to see then highly anisotropic solids when alpha is high, and low anisotropy if this value is low. So let's see how this plays out. What we have done, so this is just a recap of what I showed you on the previous slide. What we've done in terms of the pre-ceramic polymers is chosen to put them in solution with a variety of solvents. And those are listed here, from cyclooctane to p-xylene. And for these specific melting points and latent heats, we now see that this latent heat as normalized by the melting point, those values show a large variation from 1 to about 7. And so what we should expect to see then is increasing anisotropy. Now, keep in mind, we're starting with the same pre-ceramic polymer, our polysiloxanes. So in the end, we're going to end up with silicon oxycarbide, but we've made them with these very different solvents. And so what one sees now is this range of pore morphology going from left to right. Cyclooctane was basically the solvent that should show the least anisotropy, and in fact it does. These particular micrographs are basically a view looking the top down. So basically we've made a cut in the material and we're looking at the solid in this cross-sectional view. And the bottom set of micrographs are the view if we took the cut along the length of the material. And with cyclooctane, as you see here, the microstructure looks like a sponge. It doesn't matter which direction you are casting this in. It is completely isotropic. But as we move now through this increasing Jackson alpha factor, we now begin to see a great deal of difference in morphology. So for example, with cyclohexane, looking down from the top, you see these the dark areas are the pores, and they almost look like crosses. If we take the longitudinal view, we now see that these dendritic pores have these long channels here, but what you're seeing here are basically the negative of the side arms of the dendrite. So all of these pores here are now outgrowths from the main channel of the dendrite, and they're negative. If we go further, we now see prismatic pores that were produced using T-butanol as the solvent. And finally, with dimethyl carbonate, we see these lamellar pores looking down and then along the length. Highly anisotropic. If we were to look at this with water as a solvent, that fits in this region as well. So we also, just to confirm what we were seeing in the solid, we also did some imaging watching these crystals grow. And you can see from this set of images that these do correlate very nicely with the pore structures that we saw. With the cyclooctane, these are known as seaweed structures that solidification takes place along a length here, but then it can nucleate and grow in a different direction, as we see here, much as you see in seaweed. Where here with the cyclohexane and dioxane, we have these dendritic structures, the prismatic structures, and ultimately the lamellar structures in the solid. So although I have been warned by metallurgists who think about solidification much more carefully than I, that this Jackson alpha factor provides some guidance, it is not as accurate as they would like, but it certainly has given us clues in terms of the anisotropy or lack thereof in these freeze cast solids. Okay, let me just have a sip of water here. So what I'd like to do now, with that as background, I want to talk about a couple of applications. And the first will have to do with flow and filtration. And in this particular theme, we wanted to tailor pores for medicine. So what's the motivation? it has to do with sepsis. And one certainly wants to avoid sepsis. This is sometimes transmitted in a hospital, but it's a bacterial infection that one would like to avoid at all costs. And the reason is that if you look at the data, the patient survival rate actually decreases, shown here linearly by the hour. So it is, one wants to be able to identify not just that an individual has sepsis, but what is the bacteria that is causing the this particular illness. The patients with effective antibiotic therapy have a much greater sense or greater probability of survival. But the problem is, in terms of how sepsis is analyzed, is that it often takes a blood culture to do that. And that blood culture can take more than 18 hours to assess, to grow and to assess. And so time, as you see here on the left, time is of the essence. And if you have to wait for a culture, normally you are treated then with multiple antibiotics because they don't know what bacteria they're looking for. And but it would be much more effective to be able to define which bacteria it is and treat that specifically. Now, the other issue, the other challenge is if you were to look in the bloodstream, bacteria actually that could cause this illness is there at very small amounts. This is the actual fraction is zeptomolar. This is a zeptomolar concentration compared to what we see in the bloodstream. Red blood cells, 5 billion per milliliter. White blood cells, 7 million per milliliter. Platelets, 200 million. And so these are very small in contrast. And so what one would like to do is not only separate them, but separate them in a way where we can have a large enough concentration that they can be analyzed easily. So can we design a membrane to do that? And this is work that I have done in conjunction with my colleagues in chemical engineering. And on the left here is a way that some of them have been thinking about this. Can you basically produce some sort of a membrane in which you can catch these bacteria while you're flowing blood through this? And another aspect of this that's important is that it's not only concentration that's important, but it's also size. So if you look at the size of red and white blood cells here with respect to this 10 micron marker, we can think about bacteria that is about an order of magnitude smaller. So how do we deal with this? Well, in terms of the actual analysis of what could be caught in a membrane, my colleague Rustam Ismagulov has focused on digital detection methods for things like this. So he seems to have that covered. What we want to be able to do now is to grab the bacteria out of the blood, and how might that occur? And so now I direct your attention to this diagram in the lower right. So what we have here is an idealized structure of a dendritic structure shown above here, where blood could flow through this main channel along this channel here in this micrograph. And because of these side arms, if we have control of the size well enough, small bacteria compared to the larger red and white blood cells would flow through, and the smaller bacteria would be caught up in these side cavities. So we show that here schematically. And the flow in these side channels now is significantly slower than one sees through the main channel. And it's been speculated or calculated, I should say, that this is about 1% of the flow through the main channel. So what would this look like? This is an enlarged view. We started some of our experiments with colloidal particles to see if they could be caught in these side channels. And we just couldn't resist this view of the structure colorized here to show you how a small particle might be caught in the side channel. Okay, so again, how do we control that? Here's the dendritic structure that we see on freezing. This is the resulting microstructure. And again, what we're suggesting then is that the red and white blood cells would continue through the main channel here, with the bacteria particles being caught up in these side channels at very, very slow flow rates here. And as you also, another aspect of this that is important is that the number of these side channels is significantly larger than the main channels. So in terms of dendrites, this is the primary channel of the dendrite, and these are the secondary arms. So as you might expect, in terms of tuning this now, of tuning this whole process to produce a structure that we would want here, we might want to change the length. We might want to change the fraction of these arms. And to do that, we go back to our stability microstructure map that I showed you earlier to think about how we then need to be in a regime where we have dendritic structures and what comes into play. I show here an equation that defines the condition for a stable crack front. That's over here. And I do this here just to give you a sense from a solidification standpoint of what's going to play a role. Certainly the temperature gradient, that temperature difference between the cold plate and the exterior. How fast things, we see the velocity plays a role here, the freezing front velocity. But then there are other features in terms of the diffusivity of the solute in the liquid, the concentration of the solute that also plays a role in the system, and that would allow you to move here then from this stable interface to a cellular interface to a dendritic interface. So if we need to control both freezing front velocity and temperature gradient, one way to do this is not to just have a cold plate. This is an actual photograph of our freeze casting setup. So here's our cold plate on the bottom. Here's the mold. But we also put a second thermoelectric here on the top. And that allows us then to have dual temperature control in which we can program to keep both the temperature gradient and also the freezing front velocity constant. It also gives us an opportunity to move around this region. And so again, what I've shown over here is this stability microstructure map. And I've done this in a way, I've put in a few points here. We can do some experiments where we can keep the freezing front velocity constant and change the temperature gradient, or the temperature gradient constant and alter the freezing front velocity. And I want to show you both with scanning electron microscopy, but also with mercury intrusion porosimetry, which gives us a sense of the pore size distribution, where we're infiltrating mercury into the solid, and the pressure that we need to push this into the solid is going to depend upon the size of the pores. So if we know that pressure variation during that experiment, we can get the whole pore size distribution. So the experiments that I'm going to talk about use cyclohexane as the solvent. And as I said, we use polysiloxane, in this case polymethylsiloxane, as our pre-ceramic polymer. After it is pyrolyzed, we are left with silicon oxycarbide. And we looked at this with a few different concentrations. Okay, so this is what we're doing. Here's our microstructure map again that shows us that if we start here, increase the temperature gradient, one of the things that you see is that we have much smaller dendrite spacing. They're much closer together. So these are moving toward cellular-like pores. If we start over here at a high freezing front velocity and decrease it, we end up, as shown earlier, with much larger pore diameters. Okay, so these are the knobs then that we have to turn. And this is what one would typically see from an analysis by mercury porosimetry, in which we are plotting here the percent intrusion of the mercury for a given pore diameter. And we see here that at the larger scale, these are the primary pores, those primary channels. And these are the secondary pores, these side channels. And you see from a fraction of pores that the secondary pores take up much more space in the material. It's 76% of the pores are the side arms, where 24% are the main channels. And so this is an example now. If we then change the freezing front velocity, as we go to slower velocities, we're basically pushing that pore size distribution to the right to move that to much larger pores. And that's shown here in the longitudinal direction and in the transverse direction. And likewise, if I do this for constant freezing front velocity, but maintain the freezing front velocity and alter the gradient, you'll notice we aren't changing size too much, but what we're changing is how much of the main channels we have with respect to the size channels shown here. And that dendritic spacing here is a function of both those parameters, the velocity and the temperature gradient. So let's go quickly to these experiments. This is bacteria capture using a freeze cast membrane. And our colleagues in chemical engineering do this dynamic capture with this particular measurement system, in which we have a microfluidic device and an automated sampler that we can determine how much of the bacteria has actually moved through the system. And shown here again is a colorized version of the E. coli bacteria that we're picking up. We can do this as a function of just the silicon carbide, which here the capture fraction is 1 minus this value of the fraction of the E. coli that actually we pick up. And we find that basically, if we have a functionalized surface on these porous materials, we can capture a very large fraction, about 85% of the E. coli. So it's most effective at doing that. Okay, let's, I see that the clock has gone very quickly today. Let me move on now to a second theme that I want to talk about, and that is looking at materials where that could be used in energy applications because of the fact that we can deform them in a way over fracture. So these materials are known as shape memory ceramics, in which they can behave in a way that they undergo a crystallographic phase transformation. And I've shown this here schematically. Here's a stress and a strain curve. And we can start with a material that is tetragonal in terms of its crystallography. And by imposing a stress on the material, we can convert that to monoclinic. The transformation is diffusionless, which means it can keep up with the stress. It's diffusionless, so it's going to be very fast. But it undergoes significant deformation that accommodate that phase transformation. If the material is super elastic, if we unload it, it will go back and change back to tetragonal. If it shows shape memory, we can transform it to monoclinic. We could unload along this monoclinic line, and we get a shape memory response, only to get it back to tetragonal if we heat it up in temperature. So in both these cases, whether they're super elastic or shape memory, this undergoes this crystallographic transformation, large volume changes that accompany this. And there are a few ceramics that demonstrate it, in particular zirconia-based materials. And you can see this on this phase diagram of zirconia, and this is calcia. But in this region, you see these various phases: tetragonal phase, monoclinic phase, over these temperature ranges. But it's important to know that these exhibit these martensitic transformations. Okay, so there was work in the late 1980s that used that tried to produce these materials in bulk, and the problem was that the volume changes associated this were so large that the materials would just crack as they go through these transformations. So the work was dropped, and it wasn't until the mid 2000s, so 2013, 2017, where people started making pillars of these materials to study them. And the work done by Chris Xu and collaborators in Singapore showed that these shape memory effects, that they could undergo the austenitic to martensitic transformation, apply a load, heat it up, it would be restored. They showed this beautiful hysteresis in superelastic materials, and they would even try it with larger diameter pillars that had more grains, if you will, oligocrystalline pillars, and found that they'd get to a region where the diameter of the pillar was much larger than the grain size, and all of a sudden they wouldn't see that behavior where you could reverse the transformation. Instead, it would just fail. So this gave us an idea. Couldn't we do this? Couldn't we produce bulk porous shape memory materials and make the pore walls small enough that, that we would have single grain pore walls? And so we did this. Again, the idea is we did our directional freeze casting. Now we're looking at dendritic materials where we want to produce pore walls that almost look like bamboo structures, shown here in the bottom left. And again, we could do this in one of two ways. We could take our map and our microstructure map, temperature gradient, freezing front velocity that I've shown you before, and work our way over, work toward this cellular structure. And you see these materials here as they go from highly dendritic to almost cellular. There are other ways to do this as well, and that is to use coarsening. So somewhere in, we directionally solidify these materials, but then we sit them very close to the melting point of the solution. And in doing so, we can get these, the cyclohexane to coarsen in a way that it's going to impose that on the pre-ceramic polymer. So here's the coarsening process where we would freeze the material at constant freezing front velocity and temperature gradient. We've coarsened in this region and then would freeze dry and pyrolyze the material. And basically we're moving from, again, this highly dendritic structure to the porous structure, to the honeycomb-like structure with cellular pores. Let me skip this. And we can also follow this with X-ray chromatography, where we, in 3 dimensions, now watch these porous structures evolve then to these honeycomb and cellular type structures, where the dendrites result in honeycomb porous structures through coarsening. This X-ray chromatography, X-ray techniques allow us to follow this quantitatively and look at the mean curvature and how it changes, and use this now as a second strategy to tailor the microstructures. Now, when we do this, you see that the pore walls are now single grain thick. And we can then examine the stress strain behavior if the structure is dendritic. It almost has a behavior where we're loading and unloading along the same line, whereas with the honeycomb structure, we can continue to sustain higher stresses, and you see the beautiful hysteresis that is indicative of that phase transformation. Coupling this with X-ray diffraction, we can determine that the material has undergone that the transformation from tetragonal to monoclinic. And so we can monitor then the increase of the monoclinic phase with the applied stress. And if we anneal it, take it up to temperature, that's completely reversible then to the tetragonal phase, and the monoclinic phase resorts to 0. So the take-home messages here is that the honeycomb structure can sustain greater stresses because it's also inducing this greater phase transformation, and the tetragonal phase is recovering. So to finish off my presentation today, I hope I've given you a sense of what directional freeze casting can produce. And also that in terms of the 2 applications, that we can produce these highly anisotropic structures, different pore morphologies, and they can be tuned to provide good separators in flow and filtration. And secondly, albeit very quickly, we've looked at these cereodoped zirconia structures as candidate shape memory applications, and can produce a bamboo structure that is going to be robust in contrast to denser bulk materials, and survivable then in shape memory applications. So here are the folks who did all the work and who I've collaborated with on these projects. And at this point, I'd be happy to answer any questions.
Thank you very much, Katherine, for your beautiful talk and your gorgeous examples.